Okay, so this will be on permutations and combinations. Okay, make sure you spell it correctly. Permutations and combinations. Okay, permutations and combinations. First, we're going to go through some examples. Okay, suppose you take a true-false test. And guess at every answer. Okay, suppose you take a true-false test and guess at every answer. Okay, how many patterns are possible if there are 20 questions? Okay, now, for example, like if I had 20 questions, one possible pattern would be if I marked them all true. That's one pattern. If I went through and marked them all false, that's one pattern. If I say number one's true and the rest are false, that's another pattern. Okay? Now, what I want you to do is I want you to guess up here how many possible patterns are there. Okay? Think about that for a minute. Put your guess up here. Best guess. Don't take too much. Okay? Okay, write down your guess. Okay, now we're going to break it down a little bit. Suppose instead of 20 questions, we only had 2. Okay? Suppose 2 questions. Okay, if we did 2 questions, we'd have one pattern would be true, true. One pattern would be false, false. One pattern true, false. And one pattern false, true. Okay, so there would be 4 possible patterns there. Okay, and let's ditto that and say what happens if there's 3 questions. Okay, if we did 3 questions, one possible pattern would be true, true, true. One pattern would be false, false, false. Another one would be true, false, false. True, true, false. False, true, true. False, false, true. True, false, true. And false, true, false. And if you look at that, there ought to be 8 possible patterns. Now, if you go back and look at this, what I do is I look and say, okay, on this one I had 2 questions, and I just put a box for each question. Okay, I had 2 questions, and in that first one I had 2 possible answers, true or false. Okay, in the second question I had 2 possible answers, true or false. Okay, multiply them together, 4 possible patterns. On this one I had 3 questions. Each question had 2 possible answers, multiply them together, or 2 to the 3rd power would be 8. Same thing up here, 2 squared. So now, if you had 20 questions, so if I carry this on down to 20 possible questions, Each question has 2 possible answers, so 2 to the 20th power, okay? And it ends up to be 1,048,576 possible patterns if you guess at every question, okay? How close were you on your guess? Okay? Okay? And that is doing a little bit of what they call the basic counting principle, okay? Okay, let's change it from a true-false. This time, let's go a multiple choice. If you were taking a multiple choice test, and let's say on this one, it's a little quiz. Multiple choice, let's say we had 5 questions, and let's say you had A, B, C, D. 4 possible answers. How many patterns, if you guess, okay, at every question, how many possible patterns of answers are there? Okay, well, what I do is I figure out there's 5 possible questions. Each question has 4 answers, 4 possible answers. Okay, so if you figured it, you'd have 4 to the 5th power. Okay, try that on your calculator. 4 and raise it to the 5th power. Should end up with 1,024 possible patterns of answers. Okay, like if you answered all of them A, that would be one pattern. If you answered all of them B, that'd be another pattern. So even if you're guessing, you have several possibilities of patterns, okay, in your answers. Okay. Okay, so this all brings up what they call the basic counting principle, or some authors call it the fundamental counting principle. Okay. It's called the basic counting principle. Okay. It says, suppose one event can be chosen, and that would be like choosing an answer for the first question. Suppose one event can be chosen in P different ways, and another independent event, and that means for this, like what happens, what you choose on question 1 has no effect on what you choose on question 2. So they are independent. Suppose one event can be chosen in P different ways, and another independent event can be chosen in Q different ways. Then the 2 events can be chosen in P times Q different ways. So basically, the fundamental counting principle tells you you're going to end up multiplying. Okay, what you did on when we multiplied up here, when we multiplied those 2 together, and then we took it times this, we're using the fundamental counting principle. You all used the fundamental counting principle this morning when you got up. Okay, if I said, how many possible outfits can you wear to school? Okay, you go to the closet in the morning. Okay, you look in the closet. How many different shirts do you have? How many different pairs of slacks or jeans? How many dresses? How many skirts? Whatever. Okay, how many shoes? How many socks? And you start multiplying those together and realize how many different outfits. Now, some of them may not go together, you know, but you have several possibilities. And if you really want to know, you would multiply those together. Okay? Okay, so as an example, like if I said you've got 4 shirts, you've got 10 pairs of jeans, you've got 5 pairs of socks, and 2 pairs of shoes. Okay, you multiply those together, and you've got the total number of outfits that you've got to wear to school. Like I said, some of them may not go together. Okay. Okay. Another example. Suppose there are 14 people at a head table. And think about, some of you I know are involved in GAA, G Club, FCCLA. When you have your banquets, okay, and you have people sitting in a head table. Suppose there are 14 people at a head table. And they decided to exchange places before they sat down. In how many different ways in how many different ways could they arrange themselves? Okay, now this one's a little bit different. Okay, I would still do the boxes. Okay, and I'd say, okay, let's go. There's 1, 2, 3, 5, 6, 7, 14. Okay. Okay, so those each represent their chairs. Okay, now you got 14 people standing up. Pick a chair, okay? I don't care which chair. Pick one. One person sits down, okay? One person sits down, okay? There's 14 possible people that go in there, right? Any one of the 14 could go in there. One person sits down. Pick another chair. How many people can go in there? 13. One person sits down. 14 factorial. Good. 14 factorial. Yep. Okay. If you did this on the calculator, it will probably go to scientific notation, but it is actually 87,178,291,200 different arrangements. Over 87 billion different arrangements, okay, that they could, if they all move around, okay? Okay? Okay, now, take that same problem. What if they changed places? What if they changed places every second? How many years? Okay, how many years would it take? You'll never get this banquet over with. How many years would it take to go through all the possibilities? Okay, now I want you to take a couple minutes and figure that answer. Here's what you're starting with. Okay, they change places every second. I want to know how many years is it going to take. Okay, let's check. If you took, there are 60 seconds, okay, 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and we're figuring 365. We're not figuring the leap years in there. We should, okay? And if you multiply those, you end up with 31,536,000 seconds per year. So if you divide that into the, so figure the 87,178,291,200 divided by the number of seconds. Okay, and you should end up with real close to 2,764, and that's in years. Okay, you'll never get to that banquet. You'll never get there. Okay, okay. So about 2,764 years. Okay. Okay. Now, most of what we've done so far is fundamental counting principle or basic counting principle. Okay. Draw a little separator there. Now we're going to look at what they call permutations. Okay. A permutation is a selection in a definite order a permutation is a selection in a definite order of a specified number of elements from a given set. And this is the critical part. It is in a definite order. In permutations, the order makes a difference. Okay? It's in a definite order. If I said, how many permutations of 3 books, how many permutations of 3 books, A, B, and C? I'm going to label the books A, B, and C, taking 2 at a time. How many different permutations of 3 books, A, B, and C, taking 2 at a time? Okay, so here's your books, A, B, C. The arrangements, the order makes a difference. So if I said A, B was one arrangement, B, A would be a different arrangement. If I said A, C, that's an arrangement. C, A, the order, that's a different arrangement. And then B, C, and C, B. So on this one, there are 6 possible arrangements. Now that's small enough that you can write out the list if there's only 3 books and you're taking 2 at a time. And same thing, if I change this problem and I said, okay, I'm starting with A, B, C, and let's change it to use all 3 books at a time, I could actually write them out. If I did this, I'd have A, B, C as 1. If I said A, C, B is 1, B, C, A is 1, B, A, C is 1, C, B, A is 1, and the last one would be C, B, A. Whoops, sorry, C, A, B. That's another one. You end up with 1, 2, 3, 4, 5, 6 on that also. If I said take 3 books and use all 3 of them at a time, I would also get 6 possible arrangements. Okay. The problem comes out if I said, okay, I've got 1,000 books and I'm going to use 999 at a time. I don't want to have to write out. Okay, that'd be awful. Okay, so there's a formula for permutations. Okay. Okay, and the formula is Number of permutations of n elements, that would be like the total, like my 3 books, taking r at a time, that would be like if I said take 2 books. Okay, and the formula is, up in the numerator, n factorial over n minus r, that quantity factorial. Okay. Now, there's a couple things you have to know on this, and we said it earlier. 1 factorial and 0 factorial, by definition, are both equal to 1. Because you're going to end up with some 0 factorials in the denominator, and 0 factorial is not 0. 0 factorial is 1. Okay? So if I go back and I do the formula, number of permutations of 3 elements taken 2 at a time, for the books up here, I would say 3 factorial over 3 minus 2, that quantity factorial. So 3 factorial, remember it goes 3 times 2 times 1 would be 6, over 1 factorial, which would just be 1. Okay, and I get 6. If I did the number of permutations of 3 books taken 3 at a time, I'd still have 3 factorial, that's my n, and 3 minus 3, that quantity factorial. So I end up with 3 factorial, and 0 factorial is 1, so I still end up with 6. Okay. On the one that we did up above on the head table problem, if I did the number of permutations of 14 people, taken 14 at a time, okay. Now, I don't want to do all of that on the, so I'm going to do it on the calculator. So on your calculator, take on the calculator, if you look under the math key and left arrow to probability, it should look like this, and we're writing it this way, but on the calculator it shows up this way. Just kind of depends on your author and your calculator. So that's saying that you need to put in the number n first. So we need to go back, put in the 14, then go to the math key, left arrow to probability, and then pick number 2. Okay, and then we want to tell it how many people. We chose 14 people at a time. So that's the number of permutations of 14 people using all 14. Okay, and you end up with 8.7, and if you go back and look, that was our answer, but it's in scientific notation. It's putting it like 8.7178 times 10 to the 10th. Okay, 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 and you can do this same idea. Do it all on the calculator. From now on, you are not going to have to write this formula down. You're going to do it on the calculator. Okay, okay. Okay, so if I said, if I give you an example, I want the number of permutations of 10 books, and I'm going to put 6 of them at a time. How many different permutations are there? So we would put in, now, you can also do this. If you don't want to hit those numbers all the time, do second function entry, okay? And then you can go back and type over it. And I can go back and say, remember, second function entry is above the enter key. So I can make this 10, and I can make this 6 and delete that. Okay, and I get 151,200. Okay, and if I wanted to do another problem, I can just do second function entry and then type over it. Okay, okay, the last part, combinations. We're nearing the end. Okay, combinations. The difference is the order. Combinations, it's a selection of a number of elements without regard to order. That's a key phrase, without regard to order. So when you're doing these problems, you have to make a decision. Does order make a difference? Okay, and I always say for it to be a combination, it has to have at least one different element in the set. For it to be a combination, it has to have at least one different element in the set. Okay? So let's say how many combinations, if I did how many combinations of 3 elements and 2 at a time. Okay? So if I wrote them out, here's my 3 elements, A, B, C. AB is a combination. BA is not another combination. There has to be at least one different element in the set. So AC would be a combination. Okay, and BC would be a combination. There are only 3 combinations. Okay? The formula for combinations is combinations of n elements taken r at a time. You guys don't leave yet. R factorial and n minus r, that quantity factorial. You should recognize that from the coefficient of a specific term. Okay, and you're going to do this all on the calculator. So if I did this, just find it under the math key, left arrow to probability, and combinations, and punch it in. Okay? Okay.